Hey guys! You might remember in the last video where we talked about LLMs and how they're able to process text and output new text. When you talk to Claude or ChatGPT, a response seems to come in only a few seconds. But what is actually happening behind the scenes? To start, when LLMs are reading text, they can't just read it like any normal human would. First, they go through a process called tokenization. This is where the words are broken up into smaller sections. A phrase like hello world might not be split up into mini subwords because the words itself are very short. But a word like unbelievable is spread into 3 tokens, unbelieve and able. You might be wondering, why do LLMs not just take the whole word in? Why do they have to split it up into multiple pieces? Well, this is because LLMs would need to have such a wide vocabulary to fit every single word in the English language. So when they split it into subwords, this allows the vocab size to be less, and they can hold more words because a lot of words use similar prefixes and suffixes that are just put together in different orders. However, the LLM can't just take in an infinite number of tokens, which is why all LLMs have a context window, which is a limit on how many tokens they can take into one prompt. For example, Claude's Opus 4.7 can take in 1 million tokens in one request. This is a very large amount of tokens, but it's not recommended that you keep on reaching the threshold of this constantly with every single request you make into a single conversation. Saying too many things in one conversation can degrade model performance because it'll begin to forget things that you've told it throughout the conversation. However, many LLMs have improved because they're able to take in longer amounts of text and hold longer conversations without starting to forget things. And because these context windows are getting so much larger, you can upload longer documents and maybe even upload your whole code base when you're coding as a developer. And this has made it easier to innovate with artificial intelligence. However, longer conversations also lead to higher costs, because in order to keep on doing these steps repeatedly, it takes a lot of computational power to finish. So, if you've ever heard anyone say that they've reached their context limit when chatting with the LLM, all this means is that the response is just too long for the LLM to fully process and also remember. Once the words are tokenized, these tokens are converted into a really long list of numbers, and this is called an embedding. The numbers aren't just random. They're assigned based on what the word means. Words with similar meanings are also going to get similar numbers. So the words happy and joyful will be pretty close together in the vector space, but the words happy and refrigerator end up far apart because they're not as related. And the model literally understands this as distance. It'll graph it on a multi-dimensional vector, and it'll see how far away these points are from each other. You can literally do math with these embeddings too. If you take the word king and just subtract the value of man and add the value of a woman, you're likely to get an embedding that's similar to the vector queen, because that's the female equivalent of a king. The model is able to understand this because of the patterns that it's learned from the words that it's been trained on. Now you understand the 2 steps that it takes for LLMs to understand text. But there are so many different models out there that are able to understand text. So how do you determine which one is the best to use? Now, to be clear, embedding models are separate from the LLM itself. It does not generate code. Its main purpose is to just translate this code into embeddings. There are so many embedding models out there, like OpenAI's Text Embedding 3, Cohere's Embed v3. There are also open source ones like BGE and E5. How do you know which one is the right one? There's a leaderboard called the MTEB, or a Massive Text Embedding Benchmark, and it ranks every single embedding model based on a dozen benchmarks that it's tested on. You don't have to pick the embedding model that's just number 1 at the time that you see this video. You should look at the different benchmarks and see which one applies most to the use case that you want to use the embedding for. You can look at the link on the slideshow. Now let's move on. Now you understand tokens and embeddings. But how does the model actually process what you've just said? Before 2017, you would use models called RNNs, recurrent neural networks. They would read words one at a time left to right, but this would lead to memory loss, which is why they switched to LSTMs, which kind of added some memory, but it was still slow and sequential, and it would still forget things. It was pretty limited. In 2017, a team at Google published a paper that changed everything, and this talked about the transformer architecture. Every single major LLM that you use, like Claude, GPT, and Gemini, are built on this transformer architecture. Instead of reading things one by one, they read all the words at once. You're probably confused. How does it read everything at once? That's what the self-attention mechanism is. Because of self-attention, the model is able to differentiate whether we're talking about a riverbank or a bank where you deposit money, and this is based on the context that surrounds the words. Here's what self-attention does. For every word in the sentence, the model is going to ask, how do the other words affect my meaning? And then it updates the embeddings based on what it's found. Instead of processing the words sequentially, it's actually able to process the words as a web of relationships, which is why it's able to capture the real meaning of the sentence when you use a transformer model. The thing about self-attention is that it can be used with multiple attention heads. When you use only one attention head, it has to find all the patterns in one run-through. But the thing about multi-attention heads is that it's able to look at different perspectives. So one head might look at the grammar, and the other one might look at the sentence structure. Let's say you're reading an article. Having a single attention head is like one person reading the article, taking notes, and then writing a report on it. But multi-attention head is like if you had 96 people read an article and then combine their notes to make one mega article. As you can see, more heads will lead to a richer understanding of the text. Most good transformer models have multi-attention heads. For example, GPT-2, which is a pretty old model, had 12 attention heads, and GPT-3, which is still kind of old, had 96 heads. Currently, Llama's 4.0 model has about 40 heads. Okay, now we've tokenized your input, we've embedded it into numbers, and we've run it through the transformer model with a multi-attention head mechanism. But what happens next? How does it generate text? So in this example, we have a sentence that says AI is blank. And then the model generates a probability distribution of what word should be next. It doesn't always pick the most probable one, and we'll go over later on why this is, but it just picks one based on some mechanism and it adds that word to the sentence. And then it runs the whole thing again, creates a new probability distribution, and generates a new word. This process just keeps on repeating until it comes to its final word in its sentence and it decides to stop generating text. Just to recap, first the model tokenizes the input that you give it, and then it embeds it to turn it into a numerical representation that the model can understand. Then you pass it through a transformer model. Lastly, it goes through a prediction process where it generates words based on a probability mapping. In the next video, we'll cover more on different types of architectures, like the different transformer architectures and reasoning models and multimodal models. See you in the next video.